this video, we're going to start looking at Chapter 6, Thermochemistry. There's a bunch of background information that you can read in the chapter, so I'm going to kind of simplify some of those things in this video, so at some point you might want to read the chapter for further information. So there's a few laws of thermodynamics which are really great to know going into this chapter. The zeroth law is that heat flows from hot to cold objects. It flows from objects of higher temperature to objects of lower temperature if they are put in contact with each other. And it will continue to do so until they reach a thermodynamic equilibrium, at which point the temperatures are equal and constant. The first law of thermodynamics is that energy is conserved. It can be transferred in a reaction. Like a reaction can absorb energy from the surroundings, or it can release energy into the surroundings, so it can be transferred. But in all, energy is not created or destroyed. Whatever the system loses, system is usually what you're studying, the molecules you're studying, so looking at the reaction, and the surroundings is everything else. So whatever the system loses, the surroundings have to gain, and vice versa, because energy is conserved. Just like mass, there's a conservation of mass, there's conservation of mass, charge, and energy in every reaction. The second law is that in an isolated system, processes are going to be spontaneous, meaning they occur without outside intervention. But processes will occur naturally and spontaneously if they lead to an increase in disorder, which is called entropy. And that's something we're going to start taking a look at in Chapter 17. And then the third law, since we're talking about entropy, the entropy of a perfect crystal is zero when the temperature is equal to absolute zero, 0 Kelvin. Remember that the absolute scale of temperature is given the lowest possible value of temperature to be 0, in this case 0 Kelvin. So at 0 Kelvin, you basically have absolutely zero movement. Remember, temperature is a measure of average kinetic energy, so you have no kinetic energy. There's no movement of the molecules whatsoever, so we would say the entropy would be 0. Okay, so what's heat got to do with chemical reaction? So when a chemical reaction occurs, the energy of the system being what we're studying, the reaction, is going to decrease if it's an exothermic reaction, or it might increase, which we call an endothermic reaction, or it might even remain the same. For exothermic reactions, energy lost is gained by the surroundings. Remember, we said conservation of mass and conservation of energy. And energy can be lost as heat, and heat we're going to give the symbol Q. It could also be lost by work being done by the system. So if you think kind of like as yourself as a system, if you're working out, right, if you're like running on the treadmill, you're doing work, you're losing energy, and that's why you lose calories. And same kind of thing can be with a system. If your system is like expanding against a container, if it's a gas and it's expanding, it's doing work, it can lose energy that way. So if your system itself does work, it can lose energy. An endothermic reaction, the system will gain energy, and it can do so by gaining heat. That's what we're really going to be looking at in this chapter is heat. Again, heat we call Q. Or work can be done on a system to make it gain energy. And again, in this chapter, we're really going to be looking at heat more so than work. The units of energy, typically we're going to be looking at joules, a lot of the times kilojoules, which is 1,000 joules. They used to really do a lot of things in calories or kilocalories. We won't see as many questions about that on the AP as much now. But typically joules or kilojoules, but calories is another unit. Okay, so an endothermic process is one that absorbs heat. If something's absorbing heat, or endothermic, we're going to give the sign convention of being positive. So in this chapter, when you see signs, it's really about the direction of heat. So Q, or heat being positive, means that heat is absorbed or gained, and that's why this positive value. And if heat were lost, it would be a negative value. So the sign is all about the direction of heat, and the magnitude, the value, the number you see is how much. So endothermic absorbs heat. Where does it come from? It comes from the surroundings. So let's say we're carrying out a reaction in a container. okay? And you're touching that container. You have, let's say, a test tube or something, and you're carrying out a reaction. You're touching that test tube. What is that test tube, what is that surroundings going to feel like to you, to your hand? So if your reaction is absorbing heat from the surroundings is going to get cooler. The temperature of the surroundings is going to go down and get colder. So your hand is going to be sensing a decrease in temperature. Your hand is going to feel it the container getting colder. So whatever the reaction is doing, the surroundings is doing the opposite. And just remember, if your hand is part of the surroundings, so your hand is sensing what the surroundings is doing. If something's feeling colder to your hand, it actually means the reaction's absorbing heat. And an example of this is like an instant ice pack. An exothermic reaction is one that releases heat into the surroundings. Q is negative. Again, this negative and positive is all about direction. What's happening with heat? It's absorbed, then positive. If it's released, then negative. And if your reaction is releasing heat into the container is going to start to feel hot to you. It's going to feel hot to your hand. So anytime you're sensing an increase in temperature with your hand holding a container, or obviously with a thermometer as well, that actually means the reaction is exothermic. It's releasing heat, because remember, whatever the reaction's doing, the surroundings doing the opposite due to conservation of energy. Okay. Just a sidebar. Temperature, remember the definition of temperature is average kinetic energy. Remember, in any sample, all molecules are moving, and on average, there you will have an average kinetic energy, though every particle might be moving at a slightly different speed and have a slightly different kinetic energy, if you remember that Maxwell-Boltzmann distribution curve. And as the temperature approaches zero, the average kinetic energy would also approach zero, since temperature is a measure of average kinetic energy. Temperature itself is not a form of energy. It does not have units of joules or kilojoules, which we said is the unit of energy. It has units of Celsius or Kelvin. So it itself is not a form of energy, but anytime you see temperature changes in a system, it might indicate, or usually indicates, that an energy change has occurred. Collisions between particles with different kinetic energies will result in transfer of energy, and this process is called heat transfer, and this is how objects of hotter temperature transfer their kinetic energy to objects of colder temperature through collisions. You'll see this delta H a lot, and you might have seen us do delta H, or you might have seen it in past chapters, delta H, and I said skip it to this point, and now it's the point that we can start talking about it. So delta H, a fancy way of talking about delta H is saying enthalpy. Enthalpy is really just a fancy word for energy in this chapter. So you might see enthalpy of reaction, you might see heat of reaction, you might see energy, and they're all kind of synonyms of each other. Delta H specifically is the symbol given to the amount of energy, heat energy really, that's released or absorbed by a chemical reaction, and it's when it occurs at constant pressure. So there's a whole derivation of this if you want to look at your textbook, but it's beyond the scope of the AP exam. But basically, any reaction we're really doing in our lab setting is really going to be carried out at constant pressure. So delta H is really just the heat absorbed or released by the reaction. Delta H is going to be negative for delta H is going to be positive for endothermic reactions, just like Q or heat would be positive, and delta H is going to be negative for exothermic reactions. The units of delta H are really going to be kilojoules per mole. It's the heat lost or gained per mole of substances in this reaction. We'll look at that in a moment. And the sign, again, remember the sign just indicates direction, and that's something that you can get by carrying out an experiment and seeing what's happening to the surroundings. If the surrounding temperature is going down, heat was released into the surroundings, so it was an exothermic reaction, and delta H of that reaction should be negative, and vice versa. Okay, so delta H, we said, could be called enthalpy, could be called energy, could be called heat. If we want to be really fancy in our wording, and something you might see on the AP, a lot of times we call it molar enthalpy of reaction or molar heat of reaction. Sometimes it has a little subscript of RXN, or reaction, that stands for reaction. Sometimes it has a subscript corresponding to what type of reaction it is. So sometimes instead of saying heat of reaction or enthalpy of reaction, they might say heat of combustion if it's a combustion reaction, or heat of decomposition if it's a decomposition, or heat of dissolution if it's a dissolving, and having a subscript that corresponds with whatever kind of reaction it is. So let's say you have a reaction, and then afterwards you might see a delta H equals and a value with a sign. So this is telling me that 483.6 kilojoules of energy are released because it is a negative sign, and it's released into the surroundings when 2 moles of H2 gas react with 1 mole of O2 to produce 2 moles of H2O. Notice I'm following the coefficients here. And this is also telling me that since it's negative and heat's released, that the container would end up feeling hot to my hand. The surroundings would be gaining that heat, and the temperature of the surroundings would be going up. When you put delta H next to the equation, we now call it a thermochemical equation. Notice that it has units of kilojoules here. Sometimes we can write it as just kilojoules, but it's implied that it's really kilojoules per molar amount of each thing reacting. It's kilojoules per 2 moles of H2, or per 1 mole of O2, or per 2 moles of H2O. It's really just another stoichiometric quantity. It depends on the amount of reactant you start with. So if I were to change my reaction and put 2, 4, 2, 4 in front, instead of 1, 2, 1, 2, what would happen to my delta H? I would also have to multiply it by 2. It would double. It would increase by a factor of 2 as well. So delta H is really just another stoichiometric quantity. It depends on the number of moles. It's kind of like one more thing that I can now pull into doing stoichiometry with, where whenever I would touch those coefficients, I can touch those coefficients and I can also relate them to heat in kilojoules, which is pretty awesome. Again, the units of delta H are typically kilojoules per mole, but a lot of times they're just written as kilojoules, but it's implied as per mole of each substance according to their coefficient in the reaction. Another thing is when you reverse a reaction, what happens is you flip the sign of delta H. So here is my reaction, same reaction as before, this combustion reaction. If I flip it to going in reverse, delta H would be the same value, but now a positive sign. So I've kept the magnitude, but flipped the sign. If it was an endothermic, exothermic reaction to start with, the reverse would be endothermic. So equal in magnitude, opposite in sign. Delta H also depends on the phases of each substance that are there. So this is H2O gas. If I were to flip it to being H2O liquid, my value of delta H would change. You're actually saving 88 kilojoules because 88 kilojoules would have to be absorbed to convert liquid water to vapor. And if I'm omitting that step here, it's going to change my delta H value. So it depends on the phases as well. If you change a phase in your reaction, it's going to change the delta H. But hey, we can actually use delta H as a conversion factor to switch between moles and heat if we have a thermochemical equation. We have a reaction and a delta H. If you're using it as a conversion factor, just make sure you look at the coefficient of the substance that you're using. So for instance, I could say this is negative 890 kilojoules for every 1 mole of CH4, or for every 2 moles of O2, or for every 1 mole of CO, or for every 2 moles of H2O. I have to consider the coefficient. Just like as if this were part of stoichiometry, it's another stoichiometric reaction. It's part of the reaction. It's tied to these coefficients. So notice I can go between kilojoules and a mole amount of any of these reactants and products. And I could flip these coefficients if I want heat on the bottom, if I start with heat and I want to cancel it, or if I start with a molar amount of one of these substances, I can change from moles to kilojoules. Just remember, when in doubt, mole it out. If you don't start with moles, you might need molar mass to convert to from grams to moles, or if you start with liters, you might need the molar volume, if it's a gas at STP, something like that, or PV-nRT. Take a moment, try this example, and then pause the video and then check your work. How much heat is released when 10 grams of methane is burned in a constant pressure system? So all these are going to be constant pressure because at constant pressure you can relate heat directly to the delta H in the reaction. So that's really just, at this point, extraneous information because all the problems we do are going to be like that. So I'm starting with 10 grams of methane. Methane is CH4 here. And I want to turn it into heat. Remember, heat is going to have units of joules or kilojoules. Heat is a type of energy, and that's really what we're going to be dealing with. Sometimes calories, kilocalories, but mostly joules or kilojoules. So with dimensional analysis, I can just start with 10 grams. Grams of what? CH4, be specific. Okay, and if I can mole that out, then I can use this delta H, which relates heat to moles in this chemical equation. So I can use the molar mass, 16 grams for every 1 mole. Okay, now I have moles. Now I can touch the coefficient and the delta H. Remember that delta H is tied to the coefficient. Okay, so I want negative 890 kilojoules on top so that I'm in heat at the end. And I want moles of CH4 on the bottom and 1 because there is a 1 here. If there was a coefficient of 2, this would be a 2 down here, not a 1. If this were a 3 in front, it would be a 3. Okay, so make sure that whatever is going with an negative 890 is the coefficient of the substance. So it just happens to be a 1 here, but it's all based on the coefficient. And if I calculate this, okay, I get a negative number, and all that negative means is that heat's released. Since the question does ask me how much heat is released, if I wanted to, I could have just omitted the negative sign because they're already giving me the direction and just say 556 kilojoules are released. So again, positive and negative is all about direction. Negative is being lost or released. Positive is being gained or absorbed. Okay, find this example in your notes, take a moment and give it a shot. Notice this one's going in a different direction. I'm starting with 721 kilojoules and I want to turn it into grams of carbon. So that's where my delta H is going to come into play. Delta H is in kilojoules, and I can relate it to any of these substances in moles using the coefficients. It's just another stoichiometric quantity. So I'm going to start with 721 kilojoules. I'll put the sign. Why not? Because that's how much heat's released, so it will be negative. And now I want heat on the bottom so that it cancels, and I can relate heat to moles using the delta H where I have kilojoules and the coefficient of C for the moles of carbon. This is telling me that 84 kilojoules are released when 2 moles of carbon react, and that's what I'm putting into my conversion factor. Now I don't want moles of carbon, I want grams, so I have one more step to go where I use the molar mass to change from moles to grams of carbon, and then I get 206 grams of carbon, just rounding to about 3 sig figs since I have 3 sig figs in my starting number. I should never get a negative value of mass. That wouldn't make sense. So if I'm plugging in a negative heat, make sure you're plugging in your negative delta H. Or if you're removing signs when doing it, that's fine too. But make sure that your mass values are never negative. Just a note, so in these situations, like in this example that we just did before, how much heat's released when 10 grams of methane is burned? Well, what if I didn't just give you the amount of methane in the container? What if I gave you the amount of methane and the amount of oxygen? What if I gave you the amounts of both reactants? What kind of a problem would that turn into? How would I base which amount would I base my delta H off of? Well, if I give you the amounts of all the reactants there, then it's a limiting reactant problem. And the delta H is going to be based off of the limiting reactant. It's not only going to limit how much product you can make, but it's going to end up limiting how much heat can be absorbed or released as well. So here's a little note. If two or more reactant quantities are given, we must use the limiting reactant to determine the amount of heat released or absorbed by the reaction, because the heat would also be limited. So instead of finding limiting reactant by turning each reactant into product, let's turn each reactant into heat. And whichever is going to release or absorb the least amount of heat is the limiting reactant. The least magnitude of heat is the limiting reactant. Okay, so take a moment, look at this example, give it a shot. Notice how this is different from the other examples. I give you volume, pressure, temperature, which is enough information to get moles of SO2, my first reactant. And I give you grams of O2, again, enough information to get moles of my other reactant. And I want to know what's the heat that's evolved. Evolved is just a synonym of released. So I have enough information to mole out each reactant. This is a limiting reactant problem. I basically have to do 2 sets of stoichiometry where I'm turning each reactant into heat. And whichever gives me the lowest magnitude of heat is going to be the one that is limiting, the reactant that's limiting, and that's going to be the amount of heat that's theoretically the maximum that could be reached. So in this case, again, I'm going to start with the O2 just because it's, I know it's right there, okay, 15 grams of O2. Use the molar mass to mole it out. And then this is the amount of heat per 1 mole, since that's the coefficient, okay? And based off of using up all the O2, I would get that 92.8 kilojoules are released. So let's see how much heat would be released if I were to use up all the SO2. So there's 2 ways you can mole out the SO2. You can use PV-nRT, which I'm showing here, or you can see, hey, this is STP, standard temperature and pressure, 1 atm and 273 Kelvin. So you could use the fact that there's 22.4 liters for every 1 mole, and you can change liters right into moles by multiplying or by dividing by 22.4. So it's totally up to you. I'm showing it with PV-nRT this way, and you should get the same answer no matter what. So once you mole it out, then you can use that this is the amount of heat released, and be careful, for every 2 moles of SO2. So when you're using the delta H as a conversion factor, you should have for 2 moles of SO2 on the bottom. And I would find out that if I were to use up all the SO2, 59.2 kilojoules would be released, which is a lower magnitude than the 92.8. This is less heat that would be released. So essentially, this is my answer. SO2 is my limiting reactant. It limits how much heat I can make just as much as it limits how much, same way it limits how much product it can make. And my answer is 59.2 kilojoules. That's the heat that would be evolved if this went to 100% yield, 100% completion. Okay, you might end up getting the same answer if you have stoichiometric equivalent quantities to start with, and then both reactants would be completely used up. But otherwise, you're basing it off the limiting reactant always. If you have both two reactants given, you gotta do out 2 separate stoichiometry steps. Okay, and sometimes you might see the opposite. So let's take a look at this example. 5 grams of propane are combusted in excess oxygen. Okay, so I know propane's limiting, that's nice. And I tell you the heat that is released. What is the delta H for the combustion reaction? So notice here's a problem where I'm asking you to calculate delta H. In the other problems we were just doing with delta H as a conversion factor, I gave you the delta H. In this situation, I'm not giving you the delta H, but I'm giving you how much heat's released when a certain mass of C3H8 is reacted. So this is almost a little bit similar to those problems where I ask you to calculate molar mass in the past. If you remember how we calculated molar mass in the past, I said, hey, if you have grams of something and you have moles of that same quantity, you can always divide grams by moles and get the molar mass because it has units of grams per mole. This is kind of similar. Delta H is the heat that's absorbed or released per mole according to the coefficients. So it's kilojoules per mole. So if you have the heat released in kilojoules, and in this case we have grams, but if you can get the moles of the reactant, then you can just divide kilojoules by moles and you'll get the right units. Delta H is in kilojoules per mole. So in this situation, okay, I can change the 5 grams into moles using the molar mass, 0.114, and then this was the heat per 5 grams. I don't want it the heat per gram, I want the heat per mole. So if I take the heat and divide by the 0.114 moles, notice I'll now have units of kilojoules per mole, okay? And notice that I put in a negative sign here. Why? Because it's telling me heat's released. So if it's telling me heat's released, make sure that your final answer for delta H is negative. If it's telling me that heat's absorbed, make sure your final answer for delta H is positive. So I always like to consider sign kind of separately from calculations a lot of the time. I'll just, okay, released, okay, it's going to be negative, positive, it's going to be absorbed, so on. Okay, and here's my answer. Notice there's nothing I have to do with a coefficient. It has a coefficient of 1 here, so this would be correct. This would be the kilojoules for every 1 mole of C3H8, and that would go right into my thermochemical equation. So my lesson here is delta H is the heat absorbed or released per mole. Again, moles according to the coefficient. But if you're given the heat released or absorbed in kilojoules and you have moles of the limiting reactant, you can just divide these two to get delta H in kilojoules per mole. Just as a heads up, just like the last problem we saw, if you have a reaction with 2 reactants and enough information to get moles of each, then you have to just make sure you divide heat by the moles of limiting reactant to get the delta H in kilojoules per mole. So you might have to figure out what's limiting first and then divide the kilojoules that are released or absorbed by that particular moles of reactant. Okay? Remember, if heat is released, delta H will be negative. If heat is absorbed, delta H will be positive.